Solid edge simulation allows everyday engineers to test design ideas as they work. ST provides even more tools to replicate the most common operational conditions with the inclusion of steady-state heat transfer capabilities. Therefore, simulation can be used to analyze thermal effects in addition to stress, strain, force, and displacement. In this particular demonstration, we're going to model the thermal effects of a 5,000-pound truck disc brake assembly as the truck travels down this 6,000-foot mountainside. And we're going to assume that the brakes are being applied all the way down to maintain moderate descending speed. Now, in this example, of course, we could work with the entire assembly. But we're really concerned with basically two things: the temperature distribution across the rotor's braking surfaces and the stresses acting at the mounting holes on the shoulder hub. Therefore, what we're going to do is reduce what we're looking at to just the parts that we're concerned with, and that's the inner hub and the actual outer roller. So we can use display configurations to quickly change the display of the model. And then, of course, for this first analysis that we're going to run, I'm going to simply turn off temporarily the shoulder hub and just focus on the rotor at this particular time. Now, one of the key aspects of Solid Edge ST5 is the ability to create several new heat transfer study types. And of course, in ST5, as you can see, we have several. We can create a steady state heat transfer by itself, or we can couple it with a linear static or linear buckling. Now, of course, if you're only concerned about the actual thermal effects, then you can run, as I said, the heat transfer by itself. And that's what we're going to do in this first example. Basically, all I have to do is just tell it what part I want to run the heat transfer on, part or parts. In this case, we're just going to identify the rotor. Once the study has been created, we can then come over, and you'll notice that the thermal loads for ST5 have been added, and we're going to use heat flux. Basically, with heat flux, I can identify the two faces where the heat will be applied from the disc brake pads. And for our watts, we're going to use a value of 1200. Now, once they've been defined, we also want to be able to see how the part's going to dissipate all this heat, and we can define the rest of the surfaces on our rotor just by simply fence selecting. And then, of course, what we'll want to do is not include those two faces where the heat flux was applied. So I'm going to deselect those. And then, of course, for our film coefficient value, we're going to use a value of 50. And our ambient temperature, which is basically the surrounding temperature, is 20 degrees centigrade, or about 68 degrees Fahrenheit. Now, once those thermal loads have been defined, in Study Navigator, of course, it reflects those particular loads, and at any time we can turn that information off just to clear the screen up. So at this time we can go ahead and run our solve on this particular component. Now, the key benefit of digital simulation is the reduction of cost and time tied to construction and testing of physical properties. With the inclusion of thermal analysis tools in ST5, those costs will shrink even farther. Solid edge simulation broadens the capability of designers to model realistic operational conditions. Often a component under physical stress is also subjected to high and low temperatures. In many situations, it is important to account for the thermal effects, as they can play a significant role in the engineering integrity of the part or assembly. And as always, solid edge simulation uses our industry standard NXNAS transsolver to get fast and accurate results. Now, of course, temperature distribution results can show areas where the structural integrity of the material might be impacted by high or low temperatures, as you can see in this particular model. In this example, by using the probe, the results will show that the rotor is actually hottest at its outside edges, in excess of 200 degrees. Of course, if we pull a probe off on the center, you can see that the temperature drops quite a bit. But with these high temperatures, the part could warp. So we kind of feel like some edits would be necessary to drop the temperature of this particular component. But that's not a problem with synchronous technology. In ST5, design iteration is enhanced by a new tool under the Modify group called Replace Part with Copy. Now what this does is it allows the designer to make changes to a copied part without actually impacting the original component. In this case, it brings up a dialog. We'll use the name rotor 2 and save that. And you'll notice what occurs is the rotor is actually quickly replaced with the new copied component. Solid Edge's unique integrated design environment in Solid Edge lets you make modifications fast using synchronous on a single feature without having to wait for history to update. What we're going to do is we want to make changes to this particular rotor by reducing the thickness of this rib. With synchronous, at the assembly level, I can identify a face, and in this case, you'll notice all of the slots are changing at the same time. We can key in a specific value and make that change very quickly. If I want to add strength or change the design in any way, we use a tool we call steering wheel, in which you can see I can identify, in this case, the outside ring on the steering wheel, and I can add an angle to that particular rib. When that's complete, because I've removed some of the material from the rib, I might want to thicken these two plates just a little bit. By identifying that inside face, you'll notice that some dimensions in the part environment for this model appear, and so I can make those changes right here at the assembly level. Now in this case, I'm going to add a millimeter to each side, so I can key in a value of 8.75, and you can see that the model thickens up on each side by 1 millimeter. At that point, we're ready to go ahead and solve the model again. To resolve, we'll go back to simulation and tag the solve command. So downstream of the design change, the simulation results can be updated by just simply solving the model again. Design derivative performed in a matter of minutes instead of hours. Now we just simply wait for the heat transfer study to process and finish up. And then in a matter of seconds it will begin to finish this process. Here you can see it's already processing the results. And then we'll see where the temperatures hopefully have been reduced, as you can see here, from the design changes that we've made. You'll see right away that we've dropped the temperature of the rotor at its highest point about 10 degrees centigrade, and we got it under our threshold of 200 degrees centigrade. Also in ST5, we've added some display options to enhance your ability to evaluate the physical and thermal effects of the model. You'll notice under the display options we have surfaces in ISO contour, and we can also look at the model in ISO line. So if I just simply select that command, it's going to show, in this case, ISO lines on the color bar and their values and where they are applied in the actual model itself. We've also added a dynamic ISO contour tool that allows you to simply scroll, and you'll notice the arrow on the color bar changes as I scroll the value, or we can simply come over and just simply key in a value, in this case 141, and it shows where it is on the color bar as where that resides in the model. Now that we're satisfied with the results from this particular analysis or heat transfer analysis, we can close the simulation results and go to another study that we've already performed. One of the key enhancements which we mentioned earlier in ST5 simulation is the ability to couple structural and thermal analysis study types. Combining linear static and linear buckling with thermal conditions provides the designer or engineer with the ability to replicate realistic operations of the component or assembly. Now for this demonstration, we're going to display the results of a coupled linear static and heat transfer study. The study's boundary conditions are predefined. A bolted connection, you can see here where the hub connects to the rotor, was defined with 5 bolts, coupled with the same thermal conditions used earlier. Here we're looking at the temperature, which we saw earlier. But we can also view the stress where the bolted connections were made between the actual hub and the rotor as well. So the cool thing here is that the heat analysis was also applied during the stress analysis. And in this case, we can view the rotor stress where these bolt holes, around these bolt holes, to determine if any failure actually could occur from the effects of constant braking while this truck descends down the mountain. And then, of course, we can also take a look at the displacement if we want to look at that particular type of information. When we're done with this particular study or any study, you can always create a report. It brings it up and you can add your company logo, the author, the company name, and that type of information. And then you can simply create a Word document or an HTML page. In this case, I'll just create a quick HTML. You'll notice it takes a snapshot of all of the results for this particular study. And then it brings up the HTML file with hot links to each part of that particular study. So if I go down to, for example, the results and click on it, it takes us and shows us the results and those particular values, the minimum and maximum values. So a great tool to create reports for management or for the folks that are concerned about the creation of this model and whether it's going to withstand these types of temperatures under these conditions. With these new thermal capabilities, a broader set of operational conditions can be modeled. Analysis is optimized, leading to more accurate results. Designers and engineers can try out more product alternatives while reducing the material and engineering costs associated with physical prototypes. Solid Edge ST5 simulation, folks. Design better.